All right, so we're back with this reverse order of video 9 and 10. So I'm going to do 9 now. The video for 9 is talking about how to find the derivative of a natural log, which is the inverse of our e to the x function that we worked on yesterday. So one of the ways that we could prove this derivative, here you can see the derivative of the natural log is just 1 over x. Okay, so we can actually prove that using the property we learned yesterday. So I'm going to start with this. If this is our function, you should know from last year in Algebra 2 that if we take an base e of both sides, you end up with x equals e to the y. That's just me undoing the natural log. So then if I take the derivative of both sides, I get 1. And I get, well, you should know this from yesterday. What's the derivative of e to the something? It's just e to that same value. But because I'm doing it with respect to y, implicit differentiation, we would attach a dy dx. Final step would be to solve this back out for the derivative. And then I would divide by 1 over e, or I would divide by e to the y, which is that. And then I can replace this with my relationship up here, that e to the y is really just x. So after I did the derivative, I'm going to go back and replace any e to the y with an x. Hence, boom, the derivative is 1 over x. So are you going to have to prove that? No, but it's nice to see this sometimes. So there you go. And then, of course, we're going to do the derivative of natural log when there is a function inside. And so when you do the natural log of a function, you're going to do the derivative of the outside, which is 1 over the inside, and then, of course, times the derivative of that inside. So that's chain rule. We'll look at that. Before we get started, I thought I'd remind you of some properties of logs that you may have forgotten. First one is this. Let's see if you can remember this guy. This is when I have a power on the inside of my log. Any takers? The rule is I can bring that power out front and make this 3 ln x. So it's a nice way to take something that's a little more busy on the inside and simplify it. We're going to want to do that. It does change the domain, but for the purposes of our derivatives, it will be fine. Technically, if some people, if it bothers them, you could technically put an absolute value here. That's totally fine with me. Okay, the next one is this. Do you remember this guy? When you have multiplication inside of a log, that's the same as the sum of them separate. Or vice versa, if you're adding two logs, you can put them together using multiplication. And then the last one that I was thinking of, and you might see this coming, is if I have the quotient inside, I can write them separately using subtraction. Now that's helpful mathematically because then I can do the derivative of two separate items instead of having to do a quotient within a natural log, which is a busy chain rule. So again, this keeps me from having to do product rule because it separates them, and this keeps me from having to do quotient rule. So let's take a look. All right, so here I've got the derivative, or excuse me, I've got y equals natural log of 2x plus 3. So I've got a function in a function. So already going right away, I've got chain rule. So let's do it. The derivative of the left-hand side is y prime. So this has a function within a function. So I'm going to attack the natural log, the outer part first. So the natural log would be 1 over the inside, and then times the derivative of the inside. So then I attack that. That's a 2. So my derivative is just 2 over 2x plus 3. Pretty easy. All right, now let's look at this. Before I even start taking the derivative, it would probably be nice if I rewrote that to see what I'm dealing with. Now, here is a prime example. We have a power inside of a log. This is not the whole thing square rooted. It's just inside the log, which means that little guy, that 1/2 power, is going to come out front. So I'm going to rewrite this before I even start taking the derivative. Now I can take the derivative, and the 1/2 is basically just a coefficient. So derivative of natural log I'm going to attack first, then I'll attack what's inside. So derivative of a natural log is just 1 over what's inside. Chain rule then says I have to take that times the derivative of what's inside, which is 2x minus 1. So I've got 2x minus 1 over 2 times x squared minus x plus 1, which if I want to distribute that, I could, but I don't need to. Okay, same thing here. I would start by rewriting this first as x to the 1/2. And once again, bringing that 1/2 out front. And it's fine if you put that 1/2 all the way out front. This is all a product. And then I'm going to treat this as product rule. So I've got this guy times that guy. Okay, so the derivative would be derivative of the first, 1/2 times the second, natural log x. Again, if you want to put an absolute value in there, go ahead. Plus the first times the derivative. The derivative of natural log of x is just 1 over x. This is beautiful. That just becomes 1/2. This is 1/2 ln of x. Again, in the future, if you want to, you can, I think, easily see that you could factor out a 1/2. So if I wanted to set this equal to 0 in the future, I could make it a little nicer. Oh, I do. Hello. So if we want to set this equal to 0, then I could multiply both sides by 2, if you will. That would still give me 0 equals this, which means I want to know when L of x is equal to -1. How do I undo the natural log? Can think of it as base e to both sides, which gives me x equals e to the -1, or 1 over e, which is probably more likely how you'll see it. All right, hopefully, when you take a look at this guy, the first thing you should notice is there is division inside of a log. When there's division inside, you can separate them. Do you remember what with? Subtraction. So I'm going to take the natural log of them separately over subtraction. Okay, so now I'm just going to attack each one separately. So natural log, then chain rule. Don't forget the chain rule. So 1 over what's inside times the derivative of what's inside, minus 1 over what's inside times the derivative of what's inside. That -1 and the minus can become a plus in general, just to make life a little easy. And I have 2 over 2x plus 1 plus 1 over 1 minus x. Again, if I needed to set this equal to 0, let me just show you real quick. I know I didn't ask it, but let's look. Then I'd have to make common denominators. So like I'd have to multiply this guy by 1 minus x. This would get multiplied by a 2x plus 1, which is easy because it's 1. And then it would all be over this. Okay. Multiply out my numerator, 2 minus 2x plus 1 equals 0, because remember, we only look for zeros of the numerator. So this is interesting. The 2x's cancel. I get 3 equals 0. Can that ever happen? Nope, which means there would be no solutions for when the derivative is 0. That doesn't mean the derivative doesn't exist. It just means the derivative is never 0. Or for those of you who are making the connections, this would mean there's never a horizontal tangent. Something to just keep in mind. Okay, so as you're doing the problem sets, I would do everything you can to simplify your log before you even begin. Bring powers out front, split quotient rule, split product rule. All of those things will help make it a little bit easier for you to do these derivatives. Good luck.